Let's see how we can do that. We are going to see a technique called binary search. I imagine all of you have seen this before, right? But we are in any case going to recall the technique and do an analysis of it. So, the key idea behind binary search is divide and conquer, and this is the design technique that we are going to see in future classes also applied to different problems. Yeah. So, what we are doing in divide and search is really to narrow down the range of elements in which we are searching for the query, the key. And let me take you through an example. Suppose these are the elements sitting in an array, right, and these elements have to be in a sorted order, increasing or decreasing, for binary search to work. Now, suppose I am searching for element 22. What do I do in binary search? I will go and look for the middle element, look at the middle element. In this case, it is element 14, right. I will compare 14 and 22. 22 is larger than 14. So, that means that 22, if it lies in this database, would lie to the right of 14. Why is that? Because these set of elements are in increasing order. Yeah, everyone is okay with that? So, which means that the element 22 has to lie between here and here. So, we use these two variables low and high to indicate the range of the part of the array in which we have to search for our element. So, initially we had to search for the element in this entire array, but after looking at 14 we have figured out that we should now search for the element only in this part of the array. Yeah. So, now we are searching for 22 in this part of the array. Once again we are going to repeat the same thing, that is, go to the middle element, compare 22 with this middle element. 22 is less than this middle element. So, which means that 22 has to be to the left of this, which means that now we are searching for 22 in this part of the array. Once again we go to the middle element, we search for, we compare this middle element with 22. 22 is larger. So, if 22 is there, then it has to be in this particular location, and it is there. So, we can then say that 22 is at this location and return this information. Yeah, you have all seen binary search before, so this is nothing new perhaps. So, I am going to write down a recursive procedure to do binary search. This is just pseudocode, and all of you can read and understand this very quickly, I imagine. What is being done? So, once again we had this notion of low and high. Low was the lower end of the range and high was the higher end of the range in which we have to search. So, the procedure call is A is the array in which you are searching, K is the element, the key which you are searching for, and low is the lower end and high is the higher end. Yeah. Now, what is the first thing? So, if low is more than high, then basically that means that you are invoking it with something wrong. So, you just return null, which says that the key is not there. Else you go to the middle element, which is obtained by taking the average of low and high, and check if the middle element is the key you are looking for. If it is the key you are looking for, then you just return. Recall that you have to return the position where you found the key. So, you will return mid. If the key you are looking for is less than the middle element, then you know that you have to search in the left part of the array. The left part of the array has a starting location low and its ending location mid minus 1. So, you are going to search in that, and this is your recursive call to that procedure. And if such were not the case, then you would come to this else, and in this case what do you have to do? You have to search in the right part of the array, which means mid plus 1 to high, right. So, this is how you can do binary search. So, it is a small piece of code, but this is recursive. You can also write an iterative procedure for this. They are exactly equivalent, but I just so that you know how to maybe go from a recursive procedure to an iterative procedure and you understand this thing very well, I have just written down an iterative procedure also for this. Now, what is happening in our iterative procedure? The low to begin with is 1, high to begin with is n. This is elements 1 through n, let us say, in an array, and we are doing the same thing roughly, except that we are now putting it in a loop, right, and updating high and low every time, right. So, after this first step, low becomes mid plus 1 because the element was larger than the mid element. So, the element was larger than the mid element, so low becomes mid plus 1, and when the element is smaller than the mid element, then high becomes mid minus 1, and we just go through this loop till we either find the key, in which case we just return the location where we found the key, or low becomes larger than high, yeah, in which case we would just come out of this do while loop and return nil. Yeah. Everyone okay with this? Any questions at this point? So, I just shown you how to write binary search in two different ways. You can write a recursive procedure, you can write an iterative procedure to do the same thing. How much time does binary search take? Log n base 2, right? You all know that, but why is it that it takes log n base 2 time? Exactly, the size of the problem is halved at every step. So, the range of the items that we have to search in is halved after one comparison, after each comparison, right. So, if initially the range of the elements in which I am searching for my key is n, then after the first comparison it goes down to n by 2. After the second comparison, the range goes down to n by 4, and so on and on, right. So, after log n comparison, the range would go down to 1, and when the range goes down to 1, either it is that element or it is not that element, and you can stop. So, you will roughly require log n base 2 comparisons. Yes. Now, if you have an array implementation, that is your elements were sitting in an array, then you can go to whichever location you desire in constant time, right. So, then you can do the entire thing, each of these comparisons can be done in 1 unit of time in constant time, and so you can do the entire process in only order log n time. Yeah. When we do not write any base for a log n, we will understand in this class that it is base 2. Suppose the numbers in that array were not in sorted order. Okay. Here earlier till now we have assumed that the numbers were in increasing order. You can do binary search even if the numbers were in decreasing order, but if they were in sorted order, you can do binary search. If they were not in sorted order, what can you do? Suppose you are still searching for a key k, right. There is nothing else you can do but to go through all the elements, go through the entire array one element after the other, and compare your key against that. That's the only thing you can really do. Yeah. So, the worst case time then becomes order n, right, on an average also. So, if you are lucky, you might get the element initially at the beginning only of your search, but on an average you will get it, you know. So, if maybe the first time you got it at the very first position, some other element you searched, you got it at the third position. So, on average you are going to still spend order n time, right, and this is really the best you can do if the array is sorted. So, you can see there is a huge difference coming up already, right. By sorting, if you were to sort the elements to begin with, then you can search much more quickly, right. And this is a small pseudocode which is just saying that all you can do is run through the array one element at a time and compare your key against the element in the array. Okay. So, now that ends my aside on searching, right, and I am going to go back to my dictionary problem, and I am going to look at a setting where you are asked to implement, let us say, a caller ID facility for a large phone company, right. So, there is this company, and what it wants you to do is, given a particular phone number, it wants to. So, what happens in a caller ID facility? When a call comes in, based on the phone number, you can figure out the name of the person who is making the call. Yes. So, that is what the company wants to do. Given the phone number, you want to return the caller's name. Okay. Let us assume that our phone numbers are all 8-digit numbers, as is the case in Delhi, right. So, the range of phone numbers would be 10 to the 8 minus 1, right. That is 100 million, that is roughly 100 million phone numbers. Of course, the number of different phone numbers is much less than this, right. This is the range is 100 million, but maybe Delhi has only about a million different phone numbers, right. That is because not all numbers are present. So, there are n phone numbers and n is much smaller than r, right. You understand the difference between r and n. R is the range, which is 100 million, because the phone numbers are 8-digit numbers, and n is the actual different number of elements in your database, and we want to do this as efficiently as possible. Everyone understands the problem? Okay. So, you can use an unordered sequence to do this. What does that mean? That means that suppose these were the phone numbers, I have not put down the 8-digit numbers, but let us say these were the phone numbers, you could just put them in a list, yeah, in any arbitrary order. And now, how much time does searching take? Order n. Does everyone understand why? Right, because you cannot do anything else but to traverse through this list, and in the worst case you might have to go through the entire list, and so it will take order n time to search for a particular phone number. So, given a particular phone number, if you have to return the name of the person, you will have to take roughly order n time to be able to do that, right. And this is an unordered list, right. So, there is no particular order. So, removing an element. So, how does one remove an element? Suppose a particular person decides to forego his connection, give up his connection, right. So, you have to remove that particular data record from this list. What would you do? You would once again search first. You will first search where it is and then you will remove it, right. So, searching and removing, since searching itself is taking order n time, so removing is also going to take at least that much time, and you can actually, once you found where the element is, then you can just do some small modification to do the entire thing in order n time. Inserting. Why does inserting take only constant time? It is an unordered list, you do not really care where you are putting the elements, you might as well put it at the very first location, yes. So, inserting takes very little time. So, it is not clear whether this particular implementation is good for this application, but there are certain applications in which this way of doing things is fairly good, and one such application is where you have to maintain log files, right. So, when you have to maintain some kind of a log file, for instance, any kind of transactions that are happening in a database, you try to maintain log files, so that if there is any problem, you can figure out, you can revert the transaction or whatever was done. Or for instance, in your systems, you would so for system administration, you would keep track of all the various activities that were happening on your system and maintain this and maintain a log of them. So, for log files, it is very rarely that you need to do searches or removals, but you need to add data frequently to your file, right. Every time something happens, a transaction happens, you need to add. So, insertions are very frequent, but searches and deletions are much rarer, and in that case this implementation is good, because insertion takes only constant time, right. So, you really have to see between these three operations, right, which is the operation which is being performed more frequently to decide what type of a data structure to use to implement the abstract data, the dictionary data type. You could use an ordered sequence also, in which case let us say the elements we put them in increasing order of their key, right. Now, how much time does searching take? Log n. Log n, provided you had some kind of a direct access mechanism into this thing. So, used an array or some such thing which will let you go to whichever element you were looking for, whichever element you wanted to go to, yeah. So, searching takes only order log n time. Inserting and removing will take order n time now, right, because if all of these were put in an array, then if I know, so since I have to insert them in, so if I have to maintain the sorted order, then I have to insert the element at a particular location. If I have to insert it at a particular location, I have to shift everything that is to the right of the element, yeah, and so insertion will take order n time in the worst case, and similarly deletion you will have to move it back. We have seen examples of this in the previous class.
How does inserting take order n? We have to search for the position first where we need to put the object.
Right, we first have to search. So, your question is why does inserting take order n time? So, we have to first search for where the element has to be inserted, and once we know where the position is, then recall this is an array, all the elements are put in an array, right. So, we have to move, we have to create space there, and how can we create space there? We have to move everything that is to the right of that element, we have to move it one step to the right, right, and in the worst case we might have to move order n elements to the right. Yeah. So, what is order n plus log n? Order n, right. So, you have to recall your big O notation. So, order n plus log n is order n, right. So, this would make sense when you have to do a lot of searching in your dictionary, but not so many insertions and deletions from a dictionary. There is one other way which will be useful for our subsequent discussion, and that is as follows. Let us say I take an array of size 10 to the 8, right, huge array, and then what do I do? Well, Ankur had a phone number of 96358904. So, I go to location 96358904 in the array and put Ankur's name there, or whatever is the additional information associated with it, I put that in that array at that location, right.
It's at that very position.
At that very position, which corresponds to Ankur's phone number, right. Now, all operations insert, search and delete will now take only constant time. Is it clear to everyone? Why? I just have to insert a caller ID capability. What does that mean? Given a phone number, I want to know who is the person. So, given the phone number, I just go straight into the array at that location and retrieve the name. Given a phone number, I want to, let us say, I create a new phone connection. So, I take the phone number, I go to that particular location, I put the name of the person who got that connection. Similarly, if I want to delete a particular phone connection, I just go to that particular location and I remove the element there. Yeah. So, all operations take only constant time, great, right, but what is bad with this implementation? We are wasting a lot of space. Yes. So, it is not that you cannot do all of these operations very quickly, you can, but here space is turning out to be an issue.
In the second homework, you have to look at this recursive and iterative procedures of binary search which Professor Naveen talked about, and I have pasted it here for your reference. And you have to write the execution of each of these algorithms with the intermediate values of mid, low and high. And when the given value of the sorted array is this, which Professor Naveen uses here, so I have just written it out here, and your search key is k equal to 9. Okay, so you have to say that in the recursive procedure what happens to low, mid and high for the different recursive calls while you are searching for 9, and similarly for the iterative procedure. So write these two executions down, and in the next part you have to compare the time and the space complexities of these two implementations.